These two balls start at exactly the same height. One is simply dropped, the other one is launched sideways at the same instant. Which one reaches the ground first? If air resistance is negligible, they land together at exactly the same time. The sideways launch changes the horizontal motion, but does not change the vertical motion. Both balls begin with zero vertical velocity and have exactly the same downward acceleration g, and they both fall through the same vertical distance. At every instant, they are at the same height. The sideways ball has equal gaps between snapshots because there is no horizontal acceleration. Once it has left the launcher, there is no forward force keeping it moving, so its horizontal velocity simply remains constant. Vertically, the situation is different, however. Weights act downwards, so the vertical velocity changes by 9.81 meters per second every second. If upwards is positive, the vertical acceleration is minus 9.81 meters per second squared. The curved path is therefore the result of two simpler motions happening at the same time: constant velocity across and constant acceleration down. The directions can be calculated separately, and time is the quantity that connects them together. Now launch the ball at 25 meters per second, 30 degrees above the horizontal. To analyse its motion, first resolve that initial velocity into horizontal and vertical components. The horizontal component is 25 cosine 30, which is 21.7 meters per second. The vertical component is 25 sine 30, which is 12.5 meters per second. Keep those values in separate columns. Horizontally, the initial velocity is 21.7 meters per second and the acceleration is 0. Vertically, the initial velocity is 12.5 meters per second and the acceleration is minus 9.81 meters per second squared. Because the ball lands at its launch height, the total vertical displacement is 0. Use the vertical motion to find the flight time. Start with vertical displacement equals initial vertical velocity multiplied by time, plus 1/2 multiplied by vertical acceleration and time squared. Substitution gives 0 equals 12.5 times t minus 4.905 times t squared. As you'll know from Inc Maths, this has two solutions. T equals 0 is the instant of launch, so it's a valid route. The second solution, t equals 2.55 seconds, is when the ball returns to its original height. That same 2.55 seconds now crosses into the horizontal calculation. The horizontal displacement is horizontal velocity multiplied by time, so it's 21.7 multiplied by 2.55. The range is 55 meters to two significant figures. Notice what did and did not move between the two columns. We did not put acceleration due to gravity in the horizontal calculation. We did not use the full launch speed as the horizontal velocity. Only the time is shared between the two. There is another common mistake at the highest point of the trajectory. As the ball rises, its vertical velocity decreases. At the top, the vertical velocity is momentarily 0. It then reverses direction and increases in magnitude, but this time downwards. But remember, the horizontal velocity is still 21.7 meters per second. The ball is still moving, so its speed at the highest point is 21 meters per second, not 0. We can also find the maximum height using final vertical velocity squared equals initial vertical velocity squared plus 2 times acceleration times vertical displacement. At the top, the final vertical velocity is 0. This gives a maximum height of 7.96 meters or 8.0 meters to two significant figures. So the method is consistent throughout. Resolve the launch velocity, calculate the vertical motion, and use the resulting time in the horizontal motion. So far, we've been using an ideal model, a uniform gravitational field, a point projectile, and no air resistance at all. Now, if you include air resistance, drag opposes the projectile's velocity. On the way up, it points backwards and downwards. On the way down, it still points backwards, but now it points upwards as well. Horizontal velocity is no longer constant. The trajectory reaches a lower maximum height, covers a shorter horizontal range, and is no longer symmetric. The descent is steeper because drag has reduced the horizontal component of velocity. The real path is not an exact parabola. For an ideal projectile, resolve the initial velocity, solve the vertical motion, then share the time with the horizontal motion. Before using the result though, check the model assumptions. Here, weight produced the downward acceleration, while drag changed the motion. In the next lesson, we will connect force and acceleration systematically using Newton's laws and the resultant force.